I was thinking about standing there at the edge of this huge bowl in the Arizona desert. It's almost perfectly round.
It really is something else. Meteor Crater. Or, well, technically Barringer Crater.
Right, and it's massive, like 3,900 feet across. And deep, maybe 560 feet down.
That's about right. It looks ancient, but geologically speaking, 50,000 years is pretty young. It's maybe the best preserved impact site we have on Earth.
Okay, so today, let's dive into that, how it formed, this incredible event.
Yeah, the sheer force of it back in the Pleistocene, and then the whole controversy about what actually made it.
Plus why it's still so important, for space science.
Definitely. So, location first.
Yeah.
It's out there, about 37 miles east of Flagstaff, Arizona. High elevation, too, over 5,600 feet.
And 50,000 years ago, the environment was totally different, wasn't it?
Oh, yeah. Cooler, more rainfall than today. You would have had mammoths wandering around that area.
Wild. So what caused this giant hole?
It was a nickel-iron meteorite. Interestingly, it wasn't actually that big, maybe 160 feet across, about 50 meters.
Huh? Only 160 feet? But the explosion was massive.
Oh, absolutely massive. The energy released is estimated in 10 megatons of TNT equivalent because of the incredible speed, cosmic velocity.
10 megatons. Okay. And that kind of energy does strange things.
It really does. Here's the kicker. Most of that 160-foot meteorite, it vaporized. Just poof, on impact.
Vaporized, so there wasn't a giant chunk of iron buried underneath.
Pretty much no, which caused a lot of confusion later. But the impact also did incredible things to the rock.
You mean the crater rim?
Exactly. It shows what we call inverted stratigraphy. The shock wave literally flipped layers of rock Coconino sandstone, Kaibab-Moenkopi formations.
Flipped them upside down.
I stacked them in reverse order, like pancakes flipped out onto the surrounding plain for maybe a mile or two.
Wow. Okay, so that the main evidence, the big iron mass, basically vanished.
Mm-hmm.
That explains the confusion for early scientists.
Oh,
right?
yeah.
This leads straight into that whole debate.
It does. Early American settlers just called it Coon Mountain. Then the USGS, the Geological Survey, sent Grove Carl Gilbert.
And he looked around, couldn't find a big magnetic signature, couldn't account for missing rock volume equaling a giant meteorite.
Right. So he concluded, logically for the time, it must have been some kind of volcanic steam explosion. No projectile found. Must be volcanic.
But then came Daniel Barringer, a mining engineer.
Yes, and he was completely convinced it was a meteorite impact. He saw dollar signs, basically. Iron.
He thought there was a huge load of iron buried down there.
He estimated 10 million tons of it. And he spent, 27 years and a fortune trying to find it.
How much money are we talking?
Over $500,000 back then, which today is something like $9 million. Drilling down almost 1,400 feet.
All based on the idea the meteorite was just buried.
Tragically, yes. It wasn't until 1929, right before Barringer died, that astronomer F.R. Moulton did the calculations.
And figured out the physics.
Yeah, showed the impact heat would have instantly vaporized most of the impactor. Barringer was right about the origin, but wrong about the treasure.
Such a tough story. It really shows how complex problems need insights from different fields, doesn't it? Geology, physics, astronomy.
Absolutely. That kind of integration is key. Which actually brings us to our sponsor for this deep dive.
Right.
This kind of complex problem solving is something businesses face too. If you need help tackling complex challenges like with AI training, automation, software development, or even figuring out where AI agents could really make a difference for you, check out Embersilk.
They handle AI integration and strategy. You can find them at embersilk.com.
Exactly. Embersilk.com for your AI needs.
So the definitive proof, the thing that finally settled the debate, came much later.
Much later, the 1960s, with the work of Eugene Shoemaker, a geologist who basically founded planetary science.
And what did he find? The smoking gun.
He found shocked quartz, specifically minerals called coesite and stishovite. These are forms of silica, quartz, that only form under incredibly high instantaneous pressure.
Pressure you only get from
an impact or, a nuclear explosion, something far beyond volcanic forces.
So that was it. Game over for the volcanic theory.
Completely. It proved the impact origin beyond any doubt, finally proving Barringer's initial idea correct, just decades too late for him.
So the crater today, it's still privately owned by the Barringer family, right?
It is, but it's a national natural landmark and a crucial scientific site. NASA realized how valuable it was.
For the moon missions?
Yep. Apollo astronauts trained there in the 60s and 70s. It was the perfect place to simulate lunar landscapes and geology fieldwork, and it's still used for astronaut training today.
Amazing. And learning about shock quartz there helped us understand impacts everywhere else.
Absolutely. Identifying those minerals here gives scientists the key to unlock the origin of craters on the moon, Mars, you name it. It really advanced impact physics.
Which makes you wonder, doesn't it? What other big scars on Earth, things we think are just valleys or depressions, might actually be remnants of ancient impacts we haven't recognized yet?
That is a fascinating thought to leave people with. Always more to discover.
Indeed. Well, if you enjoyed this deep dive into Meteor Crater, please subscribe to the show.
Yeah, and hey, if you can, leave us a 5-star review. It really does help get the word out.
Thanks for tuning in.